exponents. If you look at our penny lab activity here, what we're going to do is we're going to look at situations that do not increase. So we are going to look at situations that behave exponentially but will decrease instead of increase. So this is called an exponential decay. We are going to start with trial 0. We have 100 pennies here. What we're going to do is we are going to dump out the 100 pennies and we're going to record on our table how many of these pennies land on heads. So here we go. We're starting 0. This is our start value, 100 pennies. I'm going to dump them out. We got all these pennies here and I'm counting them. And we did a great job and we ended up with 54 of those, in case you weren't able to count them all, turned on heads. So now I've got 54 of my pennies that I'm putting back into my cup here, right? And I'm going to dump them out again, and I'm going to once again count how many land on heads. Wow, that was a good one. So of those pennies, I had 25 of them landed on heads. So I'm going to continue this until I'm all done. So one more time. Oh, look at all those heads. 1, 2, 3, 4. Yep, that was it. 14. I'm going to do this again. And I've got 6. When I do it another time, I ended up with just 1. And then on the last time, I ended up with none because it landed on tails. So once we've filled out all of our trials, we're then going to take that handy dandy resource page here that has tosses, and I'm going to start with number of tosses when it is at trial 0. Remember, 0 is right here at the origin, and I'm going to go all the way up on my y-axis where it says number of pennies, and I'm going to do a nice supersized dot for 100. Then trial 1, you're coming down here for trial 1, and I'm plotting my value of 54. I'm going to continue that. I've got trial 2, 3, 4, 5, and you can see when I'm all done at 6, I've got 0 pennies. I know the scale is 10, so you're going to do your best to show a reasonable estimate. It's nice when you look at this. I've got a nice label on my X and my Y axis. I labeled my diagram as toss, right? Because that's what I was doing. I was tossing the pennies. You can already see from your data that this decreases, and it's a nice curve. This is explicit data because the penny will either be on heads or tails. So that's why I just have the points. If I wanted to share this and show people the trend, that's when I would take my pencil and I would just, in a very nice, gentle curve, I would try to show them how that comes down. Yep, I know, I got a little bump there. I can fix it, no worries. That's why we have erasers. So here we go. I ended up at 0. So this is what I got in my experimental data. If we go back and we look at our question sheet, it asks you, is it possible that a team conducting this experiment might never remove their last penny? Theoretically, the answer would be yes. You could, in theory, continue to toss your coin and have it land on tails. However, that would be very unlikely to occur. So we will say yes, but we will then clarify that is very unlikely. So here we go. So, would the results of this experiment have been significantly different if you had removed the head pennies each time? No, it shouldn't. Why? Because on the coin there are two sides, right? So way back when we did the probability of heads, in theory, 1 out of 2 sides is heads, right? So you've got a 50-50 chance. Every 2 flips, you would expect it to land on heads once. If it doesn't land on heads, then it has to land on tails. So the probability of it landing on tails is also 1 out of 2. So if you remove the tails or you remove the heads, you should get the same results because it has the same probability of occurring. Remember, theoretical is in theory, experimental is when we actually dump out the pennies and we do the experiment. If you started with 200 pennies, how would this affect the results? We would likely need to do more trials. Maybe we would need more than 6 trials in order to come up with 0 pennies less, but our probability is going to stay the same. So I'm just going to write down more trials. Makes sense. If we had 1,000 pennies, it would take a lot more. If I only had 25 pennies, it probably wouldn't take many trials at all. So, if we were in class, we would each take our graphs and they would be on little overheads and we would stack them, and instead of having 6 pieces of data, we would have 6, say, times 5. We had 5 groups. And we would be able to see that we would have a scatter plot where we would have all our data from our group and we would look at the overall trend. Where does the data cross the y-axis? Every single person started with 100 pennies. So we would start at 0, 100. So everyone would be in agreement that it would cross at the y-axis. Does the graph have any asymptotes? When we looked at if we looked at the data, the bigger the set of data, the more able we are to see the trend. The asymptote is where it keeps approaching but never really reaches. In theory, we would have an asymptote and it would be at y equals 0. It sort of goes back to that question in number A. Could we continue to flip our coin and never have it land on heads, right? If you take half of something, you'll always have a little bit left. So in this case, we are going to give it to it, and we're going to say yes, and we're going to say the asymptote is at y equals 0. Should the graph be continuous or discrete? We talked about this. It should be discrete. Remember, if you are counting the object and you are only looking at whole numbers, you are going to have discrete data. Continuous, you measure, you can have parts and pieces of. Is the data in this situation increasing or decreasing? It is decreasing. Each time the number of heads went down. What does this mean about the multiplier? Remember, when we're talking about the multiplier, you're looking at your y equals a times b to the x. Your b is your multiplier. That's the base of your exponent. If I'm decreasing, it's got to be less than 1. We're looking at a positive number here. We've only done positive bases. We're going to be greater than 0 but less than 1. You know, using what you know about probability and flipping a fair coin, what would you expect or estimate the multiplier to be? We would expect it to be 1/2 because that's the probability of heads. So if we're using our I know, I'm getting used to the camera. I should have slid this up a little sooner. So if we are using our format, y equals a times b to the x, right? Y is the number of heads. A is our start value. We started with our 100 pennies. B is our multiplier, right? That was our probability, 1/2. And then our exponent is X. That's how many times, how many trials we make. When I input X for 0, what will that give us? That will, anything to the 0 power will be 1. This will always give us our start value. So when X is 0, Y is 100. If you go back up and look, right? X is 0, Y is 100. That is our start value. What could this mean in relationship to our situation? It means that we started with 100 pennies. So we are cruising through this. Hopefully this is really connecting with our last unit and is just giving us a nice context. All right, so let's flip over. Now remember, our equation is y equals 100 and then 1/2 to the x power. Doesn't make sense for us to have a negative exponent. Could we go back before 0 in this case? No, we are not time travelers. If we could time travel back before we were sticking with the same pattern, it would just mean before we spilled the pennies and we had 100, it would likely mean that the previous trial, right, you would have twice as many pennies. So I could say of 200. So if we could, it would mean that we would expect to have 200 pennies before. In the context of this situation, should the domain, remember domain is your x value, of the model that we wrote, this was the one we wrote, what would it be? If we are looking at our x values, we're going to have whole numbers. Positive integers are whole numbers. What appropriate domain, with the appropriate domain, what would a graph of your model look like? So when we graphed it, they're asking us what is the shape of this model, right? We have a curved model because it is an exponential. So there's our curve. So the graph in part F looks like what graph you saw in 813. 813 is when we did those series and sequences, and then we looked at arithmetic and geometric. If you remember, arithmetic were linear, geometric, those were our exponential. Those were our curved graphs. So geometric. So what are the first few values of this function? So if you're looking not at our table, but if you're looking at this equation, y equals 100 times 1/2 x to the x power, the first few values, when I plug in, if I plug in 1, I'm going to have 50. If I plug in 2, right, 1/2 to the second power is 1/4. 100 divided by 4 is 25. Now we're not talking at this moment about the pennies. So if I then went another and I had 1/8, 100 divided by 1/8 would be 12.5. So I would keep, my reduction is by 1/2 each time, and it would keep going. And so on. So the equation, if I'm looking at a function equation, instead of using y, I'm going to use my t of n, and I'm going to use 100 is still my start value. My multiplier is still 1/2, and my exponent is going to be n. Okay, we're doing a nice job here. We've got a nice application here looking at carbon-14 dating is used to approximate the age of ancient discoveries and to learn more about things like dinosaur fossils. Scientists have studied the rate of decay of carbon-14 and have learned that no matter how much of the element they start with, only half of it will remain about every 5,370 years. Sorry, 5,730 years. So that's how long it will take for half of it to dissipate. So we call that a half-life. That's going to continue to show up. That's just part of your knowledge that you're going to have. So we're going to look at this. If we know that all living things on the planet have the same portion of carbon-14 relative to the amount of overall carbon in their body, knowing how much of carbon-14 to expect, the scientists can then measure how much carbon-14 is left in an ancient item to figure out how much time has passed since the object was living. So if we start with 100 grams of our carbon-14, right? So I'm going to go right over here. My start is 100, so I'm going to put a nice dot here for my 100 value. How much would we expect to remain after one half-life? Remember, the half-life is 5,730 years. Half of the carbon should remain, so half of 100 grams is 50 grams. After two half-lives, which is 11,460 years, I'll have half of 50 grams, which is 25 grams. And this will continue. So let's fill in the points on our graph. So 1 year, I'm going to have 50 left. And it's not 1 year, but one half-life. In two half-lives, I have 25 left. So you're going to just have to estimate that. In 3 half-lives, I'll have 12 and a half left. So I'm going to estimate that a little bit more than 10. In 4 half-lives, I'm going to have 6 1/4. So you can see I'm going to keep getting half and half and half. In theory, we are always going to have something left over. So we could fix that. We're going to draw our exponential curve. It's a decay, and it's going to go all the way down until it is running parallel nearly on top of your y-axis. So this equation for this exponential curve, if I'm looking at a function, it is still going to be that T of n. Instead of 100 pennies, it's 100 grams of carbon. My half-life, my base is 1/2, and I have to the n power, right? That is the same if you're looking at continuous. Y equals 100 to the 1/2 to the n. So this is probably the best representation because it is continuous. So if you're in between half-lives, you're still losing some of that carbon. So we're going to stick with y equals 100 times 1/2 to the, let's change that n to an x, right? Got to watch that notation there. So they're pulling it apart again. When we look at the exponential decay and we're using the function from the problem, what output do we get at when x equals 0? we are going to get an output of 100. It makes sense because our start value, in this case, was 100 grams of carbon. So according to the graph, how much carbon-14 would there be when x equals -1, right? If I'm going back, if I, instead of dividing by 2, I'm going to go back 1, I'm going to multiply by 2 because I have our negative exponent here. I'm going to get 200 for my output because that would have represented 200 grams. So if you have your calculator, you don't need a graphing one, just a regular handy-dandy calculator, and you plug in your base of 2/3, right? And then you use your exponent. Once you put in your 2, just make sure you hit the negative sign and not the minus sign. What you're going to see if you do x to the -2, right, that's 1 over x squared. So if I have, let's try our x is our -3. I'm sorry, if our base is 3 and I'm going to raise it to the -2 power, 3 to the -2, remember that's 1 over 3 squared, which is 1/9. So you should get 0.1 repeating. If I have 2/3 and it's to the -2, remember I'm taking the reciprocal, so that's going to be 3/2 to the second power. That exponent gets shared with both the numerator and the denominator. So when I square 3, I get 9. When I square 2, I get 4. So I'm going to end up with 9/4 or 2 1/4. We've done a lot with negative exponents. They're going to start coming into our application pretty soon. So remember, whenever we have a negative exponent, we're going to take the reciprocal, and when we take the reciprocal, we end up with the positive exponent. All right, so these are just little chug and plugs. We're just checking. The reciprocal of 1/5 is 5 over 1 to the first power is 5. The reciprocal of 5/8 is 8/5, and that is to the first power. The reciprocal of 1/3 is 3, and that'll be to the second power. So when we simplify, we will get 9. Sorry about this. I can see I've got 8 over 1 instead of 8 over 5. I'm sure you got it right the first time. And I'm just going to leave it as an improper fraction. Reciprocal of 2/3 is 3/2. If I cube it, I get 27 over 8. The reciprocal of a squared over b is b over a squared, and it's to the first power, right? We don't write the exponent when it's to the first power. This brings us to our last reciprocal. It's going to be y squared times z over x. It's all to the third power. I'm running out of a little bit of room, but I'm going to try to squeeze this in here. So if I have y squared to the third power, it's y to the sixth power, because I have 3 sets of those, 3 sets of z's, so z to the third, over 3 sets of x's, which is x to the third. So, congratulations, you have just watched your first online video from AG. I hope it is successful.